After this data is completed, just give me a signal. I mean, talk to me. I'll move to next slide. Got it?
Completed.
Yeah. Others. Mr. Nikhil.
Completed, sir.
మా ఇది జనరల్ క్లాస్ అవుతే మీ ఫ్రెండ్స్ పక్క నుంచి కాపీ చేయవచ్చు. Let me wait for 1 more minute. Toilet. Rian.
Yes, sir. Noted down, sir.
Yeah, good. Now this is our data. Now one condition is like no tension is allowed at bottom. Now no tension is allowed during process of our pre-stressing or due to service source application, and compressive stress is less than 12 megapascal. Now this is our requirement. In such case, what would be load that can be applied on our section? Now let us come to calculating section properties. Now for this section, we are calculating section properties: area, I value, Z value, and then Y value. Yeah, area. We have two flanges, 300 mm by 100 mm, so plus one web, 100 mm by 100 mm. The area comes to 7 to 10 power 4 mm square. The pre-stressing force, it is given as 7 numbers of 8 mm dia wires of 1000 megapascal. You getting?
Yes, sir.
7 cables of 8 mm dia, stress to stress of 1000 megapascal. So total pre-stressing force applied on a cross section is 351.85 kilonewton. Now coming to moment of inertia about centroidal axis. Since this is symmetric, now we can apply capital BD cube by 12 minus small BD cube by 12. Capital BD cube by 12 is entire rectangle. Now small BD cube by 12 is the portions which are voids, excluding our web. Got it?
Yes, sir.
So this
Yes,
is second moment of area. Yeah. So రాసుకున్న తర్వాత SS అని చెప్తున్నాండి. Section modulus. For symmetrical section, this is given by I by Y. This would be same for ZB and ZT. I mean, this would be same as ZB and ZT, which is given as I by Y, where Y would be a D by 2. The total depth is 300. 300, yeah, 100, 100, 100, 300. So I by Y. I is 658.3 into 10 power 6 by 150. 15 600. So which comes to 4.39 into 10 power 6. Now coming to our stresses. You're getting?
Yes, sir.
I want someone to be on online. No one are listening to my words. Now we do have a network problem here. I want someone, at least 1 or 2 students to be on audio mode. Yeah. P by A. Load is 351.85 here, and then area is this. So P by A comes to 5.02. Now don't try to blindly copy these values. I want you to check these values with your calculators. I don't know how many of you are doing. If this was regular class, I should have been making rounds. Yeah. The coming to eccentricity. Now you have, I mean, we are given pre-stressing cables scattered at different locations, some at top, some at bottom. As this is pre-tensioned member, you're getting, as this is pre-tensioned member, it should be prefabricated or precasted. So not only along for the service loads, so this is to be designed for handling stresses. So this is the reason why you see two extremities, like I mean pre-stressing cables at different locations in our cross section. So whenever you calculate centroid of that pre-stressing steel, which would be exactly at center of our given I section. So coming to eccentricity, now eccentricity is distance between CGC, center of gravity of our concrete, to CGS, center of gravity of our steel. Got it?
Yes, sir.
So E would be distance between CGC and CGS. Now try to remember this. We're going to use this repeatedly in coming days of our interaction. So E value, now coming to our case, now CGS lies along with center of our concrete cross section. So both are matching. So in which case E value would be 0. So you won't get any eccentricity for our cable. So you have precessing force only due to direct stress, which is P by E. Yeah. Now coming to stresses at bottom. Stresses at bottom. Now it is asked to calculate what is bending moment such that stresses at bottom is 0. Again, to remind you, we have seen many stress diagrams. During pre-stressing stage and stage 1, you see tensile stresses being critical at top.
Yes.
Whenever you come to stage 2, your service stage or loading stage, stresses at bottom fiber would be critical. So when I do take that equation, what is this? This is P by A plus PE by Z minus M by Z. So to avoid tension at limiting condition, this should be equal to 0. So when I start substituting this, I'm going to get bending moment. Now I know this value 5.2 and then I know Z value. 4.59 into 10 power 6. In which case this comes to 22.03 as my bending moment. Now I'm supposed to check whether this bending moment is correct or not. How? Now, as and when I start applying this bending moment on my cross section, on my beam, my compression stress should not surpass 12, which is given. Now let us see, check this. Now what would be stress at top? This is P by A plus M by Z. Again, P by A minus PE by Z plus M by Z. As E is 0, this is P by A plus M by Z, and this should be less than 12. Now let us check this. P by A is already calculated as 5.02. Now what about M by Z? 22.03. Got it? Now M by Z is again P by A by looking at top equation. So therefore 10.04 is less than 12. So in which case the same bending moment what can be applied such that no tension or compressive stresses are within limits would be 22.03 kilonewton meter. Got it?
Yes, sir.
Yes.
Now let us come to next example. చేసామమ్మా ట్రై టు కన్ఫర్మ్ మీ చెల్లదు అనుకుంటా ట్రై టు కన్ఫర్మ్ మీ చేసామా
చేయలేదు సార్.
యా గుడ్ మా someone should tell అమ్మా ప్రీతి can you dictate this Manjusha
Sir.
can you dictate this yep
A post-tensioned beam 200 by 300 mm.
your friend should write
Yes.
no it is not reading to me your friend should write
Okay, sir.
yeah
A post-tensioned beam 200 by 300 mm is pre-stressed with a tendon of 520 mm square area stretched to stress of 1050 megapascals. The tendons passes through a duct of 50 mm wide and 75 mm deep left in the beam. The center of duct is 75 mm from bottom of beam. Find stresses in beam immediately
after pre-stressing. It should be after pre-stressing. Yeah. Now try to check your data once. A post-tension. Now previous example was pre-tensioned beam and this example is for post-tensioned beam. Now, when you look at process, now gradually you are dealing on a case by case. In first example, it was showing advantage of eccentricity. Same cable, we are not doing anything. First example was targeted for this, showing the way in which I are going to lie our cable. So in our basic definition, we have defined like magnitude and distribution to desired degree. Magnitude and distribution is that we have same force, same cable, same steel. Now next, I mean, with some intelligence, we are locating or we are using concepts of eccentric pre-stressing. So the first example was that showing differences between eccentricity 0 and with some eccentricity. Now second example was pre-tensioned beam. Third example is post-tensioned beam. But a post-tensioned beam 200 mm by 300 mm is pre-stressed with a tendon of 520 mm square. 520 mm square area, statutory stress of 1050 megapascal. The tendons passes through a duct of 50 mm wide and 75 mm deep left in the beam, like this post-tensioned example, post-tensioned beam example. The center of the duct is 75 mm from bottom of the beam. So find the stresses in the beam immediately after pre-stressing. So this is our case. You have 200 mm by 300 mm wide beam. So this is opening in the form of duct, which is 50 mm wide and 75 mm deep. You're getting? And center of this duct, where our cable is assumed to pass at this point, is 75 mm. Got it?
Yes, sir.
Yes, sir.
So this is a picture describing the entire literature of our problem, or entire data of our problem. 200 by 300 mm wide, having a duct opening in the form of rectangle opening, which is 75 mm by 50 mm, and center of my duct is 75 mm from bottom of my beam. In this case, if you use a cable of 520 mm square, statutory stress of 1050 megapascal, what is stress induced in our beam? Can I move to next step?
Yes, sir.
వేరే వాళ్ళు చెప్పాలమ్మా.
Yes, sir.
Yeah.
Yes, sir.
My pre-stressing force. So in our examples, we might be giving, we might have given, excuse me. Are you there?
Yes, sir.
Yeah. Directly pre-stressing force might be given, or if not, stress and pre-stressing area might be given. So stress into area will give us pre-stressing force. Coming to second moment of area. Second moment of area is our moment of inertia for given cross section deducting duct space about centroid. Got it? Hello?
Yes, sir.
So moment of inertia will not be.
Yeah, will
about
not be this.
same
Will
axis.
not be this. Will not be this. Will not be this.